Clarify, closed loop, or none of this thinking is about trying to predict the future, but it's really to help us try to gain some insight and manage the system and how it works. I'm going to post an example model of influenza in a school where you can play with the parameters in there and see how closed loop thinking and these relationships can play out. Dynamic thinking. What changes will have happened as a result as this issue continues? If you get good at this, you can see ahead what patterns might occur. Trends or oscillations might occur. A good example to me on oscillations is the hog cycle. Hog prices go up, more people place hogs. You get too many hogs, the price goes down. People get out of the hog business, and so there's always an up and down cycle. However, there being some systemic changes lately in the hog cycle. As more people invest in large facilities, they can't leave them empty. The hog cycle is probably flattening out quite a bit because we don't have those changes in production. One of the challenges, I think, with dynamic thinking is that we have to usually freeze the system in order to make a diagnosis. And I think that's inherent in a lot of our language and a lot of the data we use on a farm or a problem. We say, what's the problem today? We ask, well, how many sick or dead do you have out there today? What's the prevalence rate, which is a historical measure of what's been happening? Well, we always start with a cross-sectional study, right? How many people have such and such a disease today? So that's a challenge because we start thinking static, but we've got to figure out how to get dynamic. The next thinking skill is nonlinear. We talked about that a little bit already and how exponential growth curves change over time. We ask, how does this strength of the relationships change? We assume linearity. Assumption of linearity means that each of the factors impacts the affected by a fixed proportion or magnitude. But actually, it's going to change based on the strength of a third variable. Some examples are herd immunity. We know that if we can get X percentage of the herd vaccinated, we don't have to vaccinate the whole herd, then we can cause an epidemic curve to stop, to lose its exponentiality and just go flat. A good example of nonlinearity is drug administration. And we think, a lot of folks think that if a little bit is good, then more is better, but obviously we know that's not true. Another example on the other end is the law of diminishing returns. For example, eradication, tuberculosis eradication in the United States. The last few cases of TB are extremely difficult to eradicate, and I think USDA and the states stopped too early. So now we actually see an increase in tuberculosis around the country because those last few herds could not be eradicated because folks started to dismantle the system prematurely. I think bull-to-cow ratio is another example. We talked about that. Stocking densities and infectious disease. There's a lot of examples of nonlinear behavior in the food system. Scientific thinking just means show me the data. More importantly, it means test some hypotheses. One quote from Barry Richmond is it has to do with quantification, more than measurement. An example, I think, in my mind, is a little paper we did looking at salmonella in Denmark. The blue line shows the historical level of human salmonella cases in Denmark from 95 to 2000. The red checked line was the one that we simulated had they used only on-farm control methods and made no changes in the slaughterhouse. And our hypothesis testing comes and we say, wow, there was a 19% decrease because of the on-farm control methods, and it was only 69 cases, but it was statistically significant. If we do the other scenario, which isn't shown here, what if we controlled nothing on the farm but did everything in the slaughterhouse? There's a much bigger change. So hypothesis testing, that's, I think, an example. Last one, generic thinking. How is this structure and functionality similar to others? There's stocks and states and processes and flows and inputs and outputs in almost any situation, even human relationships. The quantity of goodwill that builds up. Stephen Covey talks about the emotional bank account. You've got to, if you're making withdrawals from it, then you need to be making deposits, because if your bank account, your emotional bank account goes in the red, then you're likely to cross a threshold, leading to some unhappy relationships. Finally, someone asked the question at the Crawdad meeting where I gave a similar talk to this: does it work? Well, if you ask the question, does it work, do these models predict reality, then no, they don't. Does it give new insights or potential solutions that were previously unknown? Yeah, I think it can, depending on the problem, depending on how well you model it. Does it provide a new and common language for problem solving? I think that's definitely the case. Does it reduce intractable problems? Hopefully, if you do it right, if you all give it your best, then maybe we can fix something that we couldn't fix before. In summary, here are the 8 systems thinking skills. We would invite, we being Dr. Ricky, Dr. Anderson, Dr. Larson, to join this journey with us. One of the challenges here we're talking about is converting these skills into veterinary examples. The many examples we can get, the better, the more fun we can have, the more we can learn. I appreciate this quote, and I think this is what we're doing. To be a teacher is to be a prophet. We are preparing students for a world we can barely imagine. This has come from G. Brown, former dean of MIT Engineering. Here's a few references. There's a lot more stuff at the website. Thanks